All right, so for number 4, it says a normal population has a mean of 8 and a standard deviation of 6. What proportion of the population is less than 20? Okay, so you notice they're not talking about any sample or anything like that, just a normal population, so we know what that distribution looks like. Let's take a look at A. So if I could go ahead and draw A out, A would look something like this. We got this normal distribution. It says on A that it's, actually the whole problem, it has a mean of 8. So let's go ahead and mark that mean of 8 and a standard deviation of 6. Now for part A, it says what proportion of the population is less than 20? Now 20 is going to be to the right of 8, so let's go ahead and mark that so their picture has some accuracy to it. There it is right there. It says what proportion of the population is less than 20? Well, less than 20 is going to be to the left of it. So this is what we're looking for. If we could find the area under the curve to the left of 20, we would have our answer, which is the proportion of the population that's less than 20. Of course, we don't have a 20. We don't have tables that have these raw data points on there. However, we can convert this to a z-value, and then we can look that up on our table. So how do we do that? Well, we know that z equals the x value that we're talking about, which is 20, minus the mean, which is 8, divided by the standard deviation, which was given at the beginning of the problem. Standard deviation equals 6. And we calculate that. 20 minus 8 divided by 6 gives us 2.0. So the z value for 20 is, when we standardize that data, gives us a z value of 2.0. So instead of me jumping back and forth, I did it on the first couple problems, and we've done it in class quite a few times. I'm going to just have you look that up on your own. Look up the z table, the positive side, which is 2.0. And when you look that up, you will see, you'll see that the area to the left is 0.9772. And that is going to give us our answer, which is the proportion of the population that's less than 20. Okay, and notice that our z tables always give us area to the left, so we didn't have to take that value and subtract from 1 to get the other side, because we want the left side. We want the left side, which is this side over here. And that's exactly what the z table gives us. So the answer to that, let me go ahead and put a box around that, is 0.9772. Okay, if we go ahead and take a look at part B, and let's do that since we have some space to do that over here to the right. What is the probability that a randomly chosen value will be greater than 5? Okay, so we got the same situation, but our picture looks, of course, still is we still have our normal population. We still have the same conditions where the mean is 8, standard deviation is 6, but they're asking us what's the probability. And remember, the area under a curve can be thought of as the proportion of the population, or it can be thought of as the probability that a randomly chosen value will be greater than 5. Now 5 is to the left of 8, so we are expecting, when we convert that and look at to its z value, we're expecting a negative value. It says it'll be greater than 5. Well, greater than 5 is to the right of 5. All right, so I need to convert this to a z value. No problem. We have our equation that'll help us out with that, and that is going to be z equals the x value that we're looking for, this raw value of 5 minus the mean 8 divided by standard deviation 6. So the z value that we're going to get is going to be a negative number, negative 0.5. So this is negative 0.5. Okay, we take a look, and we look that negative 0.5 up. on our z-table, and it gives us area to the left. So that is going to give us 0.3085. That is not our answer because we want the area to the right. So we have to find its complement, 1 minus 0.3085. And when we do that operation, we get the area to the right, which is 0.6915. That's the area to the right of 5, or the z-value of negative 0.5. So our answer for problem B is 0.6915. All right, let's move on to number 5. Number 5 says, find the area under the standard normal curve to the right of the following z-values. Round your answer to 4 decimal places. Find the area under the standard normal curve, and that's to the right of. So these are already z-values, so we don't have to turn them into z-values. That's kind of nice. Let's do part A right here. And if we take a look at that standard normal curve, it looks something like that. It's a little bit sloppy, but it'll do today. And it says, well, if it's a standard normal curve, our mean is always going to be 0. And to the left is this negative 2.47. And we want it to the right. So if I want to the right, that's going to be over here to the right. This is what we're looking for. All right. Yep, good enough. I can't help myself. A couple more. And when I look this value up on the z-table, of course, it's going to give us, as the z-table always does, it gives us area to the left, which is a very small area, 0.0068. I don't want the area to the left. This problem said area to the right. So I have to take 1 minus that very small area, 0.0068, and that will give me the answer, which is a large area, most of this distribution, which is 0.9932. And there it is. So let me go ahead and box that answer, 0.9932, a little more than 99% of that area under the curve. Okay, so let's do part B. How much space do I have? I'm going to go ahead and do part B right here. Part B says find the area under the standard normal curve to the right. Again to the right, but this time, let's see, there's our mean at 0. But this time we're to the right, so it's what, 1 point, I don't know, I'm going to estimate, it's probably about there, 1.31. It's a positive z-value. Positive z-value, boy, it's not sticking here. Let me try that again. It says it wants it to the right of this, so we are trying to figure out the area to the right of that z-value of 1.31. I look it up, and of course, the z-table gives me the area to the left. Darn, I want it to the right. I get 0.9049 to the left. What do I have to do to get the area to the right? Find its complement, 1 minus 0.9. Can I squeeze that in? 9049. When I take that subtraction from 1, I end up getting 0.0951. Let me write that down here. The answer is 0.0951, and that is the area to the right of a z-score of 1.31. Let's take a look at number 6. It says a population has a mu, or a mean, of 23 and a standard deviation of 20. Let me highlight this. Let's find the mean of the x bars. So that's the mean of the sample means. And if we look at our notes, we've got this central limit theorem. For some reason that note is not showing everything there. Let me see if I can get it to show better. There we go. So central limit theorem says if we have our sample size is bigger than 30, and it is, sample size is at 100, then these characteristics follow. These things are true. And it is that our mean of our sample mean is going to be equal to the population mean. Well, it tells us at the very beginning that the population mean is 23. Well, if that's our population mean, then that's also the mean of our sample means. So this is going to mean, that's too many mean words in there. This is going to mean that the mean of our sample means is 23. Now, how do we figure out our standard deviation of the sample means? Let me see if I can get another color to work here. So we want the standard deviation of our sample means. And look at that. Our central limit theorem for the sample mean shows up again to the rescue. And we can figure this out by taking, let me write this down, the mean of our sample means is going to be equal, it says, to the population mean. There it is. It says the population mean and the standard deviation, population standard deviation. So I said population mean, I misspoke. The standard deviation of the sample means is equal to the population standard deviation, which is given up there at, and here it is, you can see, 20. And the formula says that we need to divide that by the square root of n. Where is n? Let's get another color. N is sample size 100. Well, those numbers are nice and convenient because we know the square root of 100 is only 10. And anyhow, when we take a closer look and divide that, we get 20 divided by 10, we get a 2. So the standard deviation of the sample mean is 2. All right. Let's take a look at another one. Coffee. The National Coffee Association reported that 61% of U.S. adult drinkers, 61% of U.S. adults drink coffee daily. A random sample of 250 U.S. adults are selected. So something to note here is that they're saying this is the National Coffee Association reported. This number right here is actually talking about the population. Okay, so this is the population. Now, what are we talking about? Population mean or population or sample or proportion of population? You know, what's going on here? And when you take a look at the rest of the problem, part A is saying we want the mean of the sample proportions. So we're talking about the proportion. Up here, the National Coffee Association reports that the population proportion is 61%. Now we can write that, population proportion is just lowercase p. We could write that as a decimal, so p equals 0.61. All right, so did I put the central limit theorem? Okay, the central limit theorem for proportions, I'm not sure if I copied that. There it is right there. We can bring this up actually, if it'll let me. Will you let me? There it goes. So let me bring this up a little higher just to kind of highlight what's happening here. Maybe I need to make this a little bit smaller as well to squeeze all this information in here. Work with me, Apple iPad. So it has these assumptions here that n times p must be greater than or equal to 10, and that n times the complement, and I'm talking about this right here, must be greater than or equal to 10. This particular problem doesn't ask us to prove that. It's always a good idea to do that, to go through that piece, but as you know, we talked in class that some of the ALEKS questions don't actually ask that. Okay, so the next piece here is it says that's important for us to see. Let me get a little color here, highlight with maybe red. It's telling us a similar thing that the last central limit theorem, except this is for proportions. It's saying that the it's saying the mean of the sample proportions is equal to the population proportion. Well, that is awesome because we want the mean of the sample proportions, and we know the population proportions, so therefore we know this as well. This is 0.61. And then for part B, it's asking for the standard deviation of the sample proportions. Oh, I've got that as well right here. So I can work that problem using this formula. Let's see if we can do it. I'll do that in green. I'll see if I have space to work that problem. I think I'm going to work that problem over here. This is going to be part B. Let me zoom in and try to fit it all in here with a little smaller pen tip size. So remember, this is going to be the standard deviation of the sample proportions, and that's going to be equal to the formula down here that I already lit up in green. So now that means that we take the population proportion, which is 0.61, times its complement, which is 0.39. We divide it by the sample size of 250, and then that whole thing must be, and don't forget this part, square rooted. This is now going to leave us with the standard deviation of the sample proportions is approximately equal to 0.0308. And it may say how many decimal places to take here. Let's take a look and see if we can see that. Does not say exactly how many decimal places. Let's go ahead and go to 4 places. Of course, I'm going to be lenient if they don't tell us. Just show me your work so I can see what's going on. I'll go to 4 places, but they're not being very specific. 0.0308. There's that solution. Here's our first solution in part A. And now we will need to take a look at part C. It says find the probability that more than 65% of the sampled adults drink coffee daily. So now what we're going to do is we're taking the sampled data. So we're making a sampled sample distribution basically, and we know that by the central limit theorem that if these assumptions are met, that this sample distribution will be normal. And so let's take a look at that. Take a look at the picture. There's my sample proportion, and by the way, these are p-hats we're talking about. And this is a distribution of p-hats. So it says find the probability that more than 65% of the sampled adults drink coffee daily. Well, first of all, I think I want to mark down, because I like to, the mean. And the mean is going to be this guy in red that we found, which was 0.61. Now they're asking us find the probability that more than 65. Well, 0.65 is to the right. So there's my 0.65. I think I'm going to try that again. There's my 0.0. That didn't work out either. Try that one more time. Otherwise, I quit. I quit. What is going on? Let me try that again. That is 0.65. I said I was going to quit, and I lied. I guess I'll keep on going. So that's 0.65, and it wants the probability that more than, that's going to be to the right. If I could find the area to the right of that, I've got my answer. I've got the probability that more than 65% of the sampled adults drink coffee. So what do? Well, I've got to change this to a z-value. Is that going to be hard? Not really, because I got this nice little formula over here that says that z equals p hat. And what is p hat? Do I have p hat? P hat is going to be, I'm going to keep the same color. It's right here. It's 0.65 minus, and then it says, what does it say? Minus p, which is my population proportion, which is also the mean of the sample means, which is in red, 0.61. So then I divide this by, what does it say? There it is. The standard deviation of our sample proportions, well, that's the value we just found in green, and that's 0.0308. So then I go ahead and I do the math, put it in the calculator, and I get z is approximately equal to 1.2987, and this goes on. But our z table only has 2 values, so let's go ahead and look it up as Let's round to 2 decimal places. Let's look at that 9, and oh, the right is bigger, 5 or larger, so let's round this guy up to a z-value of 1.30. So now that its z-value, we standardize it, we got the z-value. We look that up, 1.30, and we get an area to the left, as we always do with the z-table, is 0.9032. I don't want that. I want the area to the right, so I just say 1 minus that. 1 minus 0.9032, and I then get my answer. I'm just really getting out of space, so let's see if I can squeeze that in there. I get my answer, that's a 2. I get my answer, which is 0.0968. Let's go ahead and try to lock that in a little better. Not lock that in, but box it in to make it clearer to see the answer. That once again is 0.0968. Okay, what else do we have to do? That was A, B, C, and then it jumps to F. All right, whatever. Can't do our alphabet here, it looks like, but that's okay. Next problem is what? Would it be unusual if less than 54% of the sampled adults drink coffee daily? Okay, well, basically what we got to do is we have to do that same problem again, except using the new data, which is this. Okay, not the new data. It's still the same situation, but instead of asking 65%, they're asking 54%. So what is that mean? That mean is still 0.61 or 61%. They're asking us about 54%. That's to the left out here, 0.54. There it is. They want us to know, and actually that drawing is not the best, really. But, you know, we don't have to have that was too much. We don't have to have these perfect drawings. We just want to kind of know if something's to the left and right and things like that, so we keep it straight. But I think I'm going to go down. I think 54% is a little further down the line, something like that. So this is 0.54. All right, and they want to know, would it be unusual if less than that? So we're talking about the tail here. Now, it would be unusual if the area under the curve here, area to the left, is less than 0.05, then we consider it unusual. So let's see what it is. Of course, we need to figure out the z-value. So let's do that real quick. Z equals the data point, which is it's really the sample. It's really the sample proportion of 0.54 minus the mean, which is 0.61. We have to divide that by the standard deviation of the sample proportions, which was in green at 0.0308. Let's go ahead and use our calculator, subtract, then divide. We're getting, I don't know, z equals negative 2.27, and this is repeating. So we're just going to take negative 2.27. So we're going to use this z-value and look that up. And the beautiful thing here is it gives us, because the tables always give us area to the left in terms of z-values, it's going to give us the area to the left, exactly what we're looking for, 0.0116. Now, is that unusual? Yes. Yes, it would be unusual. Yes, it would be unusual if less than 54%. I should restate all that, but I think I'm going to run out of space. Yes, it would be unusual. And I'm going to chicken out and just say because we got, what, 0.0116, and that is less than our sort of rule of thumb of 0.04. So because of that, this is unusual. Yes, it would be unusual. Let's go ahead and put a box around that. If I wanted to say a little more, I might say it would be unusual if less than 54% of the sampled adults drink coffee daily, comma, because the probability is 0.0116, which is less than 0.05, which is our general rule of thumb that our criteria for something being unusual. Let's take a look at number 8. Number 8 says construct the 98% confidence interval for the difference between two populations, population 1 and population 2. Now they give us x sub 1 and n sub 1 and x sub 2 and n sub 2. So these are just the two different populations. If you take a look, if you ever want to know the formulas, right, you see this and you go, what is this? The difference of two proportions. You go to our formula sheet and there it is right there. Yikes, that thing looks like a beast of a formula. It kind of is. But, after doing a bunch of these problems, really it's just the point estimate minus, and then over here it's the point estimate plus, and then it's the margin of error, which is the same thing on both sides. So there's a lot of redundancy. So really all we really need to do is figure out our standard error, multiply it by our critical, and then we've got our margin of error, and really the rest of the problem kind of just falls into line after that. But let's go ahead and do that. So I went ahead and copied that for us. That is our standard error. Before we do that, I think we need to do a little bit of organization, organizing basically our information. And I'm going to zoom in because I don't have a lot of space here, and I'm going to run out of space. Let me go ahead and change the pen tip size and go to red. I'd like to go ahead and organize my information, and what I'm going to do is I'm going to underline my first population in red. So let's do this over here. This is population number 1, and maybe I can go with a little thicker. Population number 1, what did I find? I found that the x value, x sub 1, what did I find? X sub 1 is what, 56. And I found that the sample size from the first population is 146. 146, that would be n sub 1. So once you have x sub 1 and n sub 1, you can get your sample proportion from that first population. And that's just going to be x sub 1, 56 over n sub 1, 146. And divide that, we get approximately what? 0.384. Good. Okay, let me write down here, maybe make it a little clearer, that our p hat from our first population is approximately 0.384. I think I'm going to put a circle around that. And I just messed up my p hat. There we go. So now let's go ahead and look again. And let's organize our information. This is our second population, right? So x sub 2 is 85. X sub 2 is 85. And n sub 2 is 117. 2 is 117. And so we can get our p hat from our second population. That's going to be 85 out of 117. Go ahead and divide that. I'm getting approximately 0.726. And I was telling you that, when we're doing this part of our equation, we're going to have to get its complement and everything. So I think it's appropriate to go to 2 decimal places even, but 3 is probably better in this case. You don't have to have 4 decimal places here. But we did find our p hat, our sample proportion from our second population. That's approximately 0.726. I'm going to put a little circle around that. And remember, I need to get my my point estimate. Now the point estimate is just found by taking those 2 bits of information. Oh boy, I'm going to run out of space over here. I'm going to write my point estimate over here to the right. I'm going to say my point estimate is, my point estimate is going to be, my point estimate is going to be p hat from the first minus p hat from the second. And that's just simply taking the first, which was in red, which was 0.384, right? Yeah. And then the second minus the second in green, The second in green was 0.726. And we're just following their directions, right? It says p sub 1 minus p sub 2. So we've got to take the first one minus the second one. And it's going to give us a negative value. That's okay. Don't freak out. It told us to do this, so you got to follow that. P hat sub 1 minus p hat sub 2. This is going to give us our point estimate, which is negative 0.342. I'm going to put, I think, a box around that. That's a really important number, which is our point estimate. Now we need to work on this beast right over here, which is talking about the standard error. I'm going to go with another color here to highlight the standard error. How about we go with purple? So this is the standard error. So let me write right here. Standard error. Now standard error, I've got, let's say something, I got a phone call coming in. Okay, standard error is going to have, you can see p hat sub 1. So I'm going to go ahead and change my color to red. And I've got p hat sub 1, which is, all right, we had it over here. P hat sub 1, which is 0.384. So I've got 0.384. Now I need to multiply it by its complement. Its complement is 0.616. Uh-oh, am I going to run out of space? I'm definitely going to run out of space. Let me start that one again. So it's going to be 0.384. I'm taking this piece right here from my formula. I need to multiply that by its complement, which is 0.616. I need to divide that by the sample mean from my first population, which is right there at 146. Okay, then I must add that to my second population. I'm going to do that in green. I'm now on this part of the equation, p hat sub 2, which is 0.726. 726 times its complement, which I'm really getting pressed for space, 0.274. Yikes. That's divided by the sample size from our second sample, 117. 117. Don't forget to take the square root. You got to be like the master of your calculator to do this thing, right? You got to multiply, divide, add the two together, depending on your calculator's memory, and then take its square root. Don't forget the square root. And we're getting here, I don't know why I did this in purple, but I'm going to continue. We're getting that our standard error is this guy. So our standard error is going to be approximately equal to 0.057626. That's a lot of that's quite a bit of detail there. Let's get our margin error, and I don't know if we have to go to that much detail, but I guess I have it there, so let's keep it. We also need, don't forget, we need to get our point estimate. So our margin of error is going to be equal to our point estimate. What is our, I'm sorry, not our point estimate. Our margin of error is going to be equal to our critical. Now getting a critical on this particular problem is not too rough. Remember, be careful. Do you use, go to the formula sheet, is our critical going to be a z value or is it going to be a t? And you can see right there for this formula, it is a z value. So if it's a z value, it actually is pretty easy to find because we can use this handy dandy little chart. That particular problem said find a 98% confidence interval, and 98% is right there. So for this particular 98% confidence interval, half the z sub half of alpha, right, which is its critical, is going to be equal to 2.326. That's our value we're going to use. So let's go back up to the problem. See if I can find it. There it is. There it is. So it's critical that we got was 2.326 multiplied by the standard error, which was, I guess I'll do that in the color that I had, which was in purple. So I just found out was 0.0576226. So the margin of error is approximately 0.134030167. Okay, now we go for the answer. I'm really running out of space. We go with our point estimate. What was our point estimate? It was in black right here at a negative, there's negative 0.342. So let me see if I can squeeze this stuff in here. Negative 0.342 minus the margin of error. And I'm going to now cheat by copying that. I'm just getting so tired. Let's see, copy and cheat, paste. There it is, right there. Uh-oh, can I fit it all in? I think I have too much detail in this. Now this is going to be the population portion of the first minus the population portion of the second. And our confidence interval, once again, our point estimate, 0.342. 0.342. Now plus the margin of error. Oh, it's going to overlap probably. Paste. Darn it. Oh, and I made it so tiny, no one ever will be able to see it. Make it just a little bit bigger and see if we could squeeze it right there. Okay, so then, of course, we subtract. Oops, we subtract. I think I'm going to round it to 3 decimal places. I get negative, I'm going to make it a little bigger so everybody can see it, 0.476. And this is the difference of those two populations and its proportions. And then when I add the point estimate plus the margin of error, I get approximately negative 0.208. All right, so that is my confidence interval. And I actually like to also say this is at a confidence level, CL, of, and what was that, 98%. So the reader knows, what confidence level it is when they look at that. Okay, let's take a look at number 9. Number 9 says a sample size of 72 is drawn from a normal population whose standard deviation is 5.4. The sample mean is x bar equals 50.91. So construct a 98% confidence interval for the mu, right? The mean, population mean. Round the answer to at least 2 decimal places. Okay, so what this is number 9, confidence interval. So we have to kind of go through and do a little bit of, investigative work, something like that. We got to figure out, okay, it says we need to find a confidence interval for the population mean. We got 2 formulas for that, okay? 2 formulas. Now, this one has a population standard deviation. Well, we only have 1 formula for that. We have 1 formula, it's right here. I'm looking for the confidence interval for a population mean, and the standard deviation is known. The other one is standard deviation is unknown, and so we have to use little s, which is sample standard deviation. Okay, so this is what we're working with right here. Notice it uses the population standard deviation, and it also uses a critical value that's a z value, which is going to be much easier for us to look up. In fact, we look it up on this chart right here. Okay, so let's do this problem. All right, number 9, some of the little pieces and parts that we know. We know that, I think I'll use a color. We know that our x bar, is 50 0.91. Remember in our formula, that's going to be our our point estimate. Now we also need to know what our critical is. Our critical, remember we just looked that up like we did before. Z of half of alpha. This is for a critical of 98%. And that's going to be, if you look it up on the Z, it's what did it just do? Something funny. 2.326. That's for a critical of, let me put a little note of 98%. Remember how we looked that up? Look up 98%, 98%, 98%, 98%. There it is. There's our critical for 98%. 2.326. So there it is at 2.326. Okay, so we've got that. Now what do we need? We need our standard error. This is what we did before, but these problems are definitely much more simplified. If you look that up, the standard error is easier because it's just going to be our sigma, population standard deviation, of 5.4 divided by the square root of our sample size. The sample size they told us sample size, we'll do that in blue, was 72. Okay, put it in the calculator, and what do you get? Standard error is approximately 0.6363961. Multiply the critical and standard error. So this is going to give us the margin of error. Multiply the critical, which was in purple, 2.326 times the margin of error, which is right here at 0.6363961. I'm going to get a margin of error of approximately 1.48027. That's more value than you need, but that's okay. And remember, how do we actually get this value? It's going to be a point estimate, 50.91 minus the margin of error. I think it's time for me to copy and cheat. Minus the margin of error. Copy, paste. And we're trying to get a confidence interval for the population mean. So there's our symbol there. And then we've got our point estimate again, which happens to be the sample mean, which is 50.91. And now it's going to be plus that margin of error. So let's go ahead and calculate it. We're going to round this to, it says at least 2 decimal places, and that's going to give us approximately 49.43. And our upper bound or limit, or however you want to call that, is going to be approximately 52.39. This is at a confidence level of 98%. And there we go. Number 10, it says, how many more do I have to do here? Man, it is late. I just got back into town. Man, okay, number 10. Number 10, it says a sample of size 86 will be drawn from a population with a mean of 90 and a standard deviation of 24. Use the basically distribution table if needed. So this is a normal distribution table. So find the probability that X bar will be greater than 89 around the final answer to at least 4 decimal places. So okay, so we've got to, we really need to properly label our information here. It says a sample size of 86. So let's go ahead and write over here. We know, let's see, where's this best space to work here? We write it over here. We know that N has a sample size of 86. So a sample size of 86 will be drawn from a population. Okay, now they went back and said population. So that was a sample, but that's drawn from a population, and that population has a mean of 90. Let's use the proper notation. The proper notation would say the mean is 90. What's the notation for that? Well, that's a mu. Population mean is 90. And it has a population standard deviation, which is 24. So this is the central limit theorem is what we're using for this problem. And, you know, if their sample size is larger than 30, so we can use this. And something that's real important to see is, what color am I going to make it? Blue this time. Something important to see, blue, is that the mean of the sample, the mean of the sample means, because it says find the probability that this sample means. So I want to know what the mean is. Helps me draw a nice picture. But it says that the mean of the sample means is going to be the same as the population mean. Well, that's the population mean. So I think I want to take a little note over here, just to kind of get some things straightened out, that the mean of the sample means is going to be equal to the population mean, which is 90. Okay. Also, what I need to know is I need to know about this, let me use this color, green, that this standard deviation of the sample means is going to be the population standard deviation divided by the square root of n, the square root of our sample size. So this is going to be real important for us to figure this out also. The standard deviation of our sample means is going to be equal to 24, right, our population standard deviation divided by the square root of the sample size, which we found out in red was 86. So now we know that the standard deviation of our sample size, of our standard deviation of our sample mean rather, is approximately, let me try that again, 2.58799. Now we need that because I need to know what this z-value is. And this z-value is going to be calculated by this formula that I just checked down here in the bottom corner, right there. And that is that x bar, what's our x bar? Do we have an x bar? Well, what they're talking about, if I drew a picture for you, which I guess I will, they're talking about this guy right here. That this is the distribution of little x bars, okay, of the sample mean. And I found out that the mean of the sample means is in blue up there, which is 90. And they're asking us, what about, find the probability of x bar, that the x bar will be greater than 89. 89 is to the left of this, so we'll put it right here. I'm going to say this is 89. And they said greater than 89, that's to the right. All right. Don't have a particular table for 89, but I do for z values. So I take the x bar, which is 89, subtract it from the mean of the sample means, which is 90, divided by the standard deviations of the sample means, which was 2.58799. And when I do all that, I get z is approximately equal to, approximately equal to negative 0.39. So this is negative 0.39. I looked that up on my table, z table, and I get 0.3483 0.3. Of course, that's not what I want. I want the right side, so 1 minus 0.3483. And I get my answer, which is 0.6517. Let's see. So if I were to describe this, the answer would be the probability that x bar will be greater than 89 is 0.6517. Don't have a lot of space really to write all that. I'm just going to write down the answer that I found, the area to the right, which happens to be 0.6517. Probably better practice to restate the question, but there it is. Okay, let's take a look at the next problem. And the next problem is number 11. Suppose that the antenna lengths of woodlice are approximately normally distributed with a mean of 0.2 inches and a standard deviation of 0.05 inches. What proportion of woodlice have antenna lengths that are more than 0.27 inches? Round your answer to at least 4 decimal places. So if you're wondering where this belongs in our problems, this is before confidence intervals. This is in chapter 7, when things were maybe a little bit more on the simple side, but it's telling us all that we need to know. It's telling, we're not doing any samples, right? So there's nothing to do with samples. They're just telling us that lengths of woodlice antenna, they're approximately normal when we look at the distribution of the antenna lengths. So that means it's going to have the look of a normal curve, right? Standard normal curve. Well, this is an approximately normally distributed situation. It tells us right away that the mean, right, there it is, the mean is 0.02 with a standard deviation. Go ahead and put some color on that so we can find it, of 0.05. What proportion of woodlice have antenna lengths that are more than 0.72? Well, 0.72 is to the right of 0.2 or 0.20. So let's call this not 72, 0.727. See how tired I am? It's almost 12 o'clock and I've been gone out of town. I'm very tired. I'm actually starting to get delirious here. But anyways, we'll keep on going. So it says find the lengths that are more than 0.27. Well, more is to the right. And if I could figure out this area, I got myself an answer. But what I really need to do is I need to convert this raw score into a z-score. So I take that raw value of 0.27, subtract it from the mean, which is 0.2 or 0.20, divided by the standard deviation in green, 0.05. Well, that gives me a z-value of 1.4. So this z-value is 1.4 or 1.40. Look that up on the table. Of course, that always gives us area to the left, 0.9192. That's not what I want. I want the area to the right, so 1 minus 0.9192, and it gives me my answer. What's the answer? The answer is 0.0808. Go ahead and write that a little larger over here. 0.0808. All right, let's move on. Number 12. Calcium levels in people are normally distributed. Yay. That means I get to use the standard normal curve with a mean of 9.5 milligrams per DLs and a standard deviation of 0.3. Now, individuals' calcium levels in the bottom 10% of the population are considered to have low calcium levels. Find the calcium level that is the borderline between the low calcium levels and not considered low. Carry intermediate computations to at least 4 decimal places. That means don't round more aggressively or smaller than 4 decimal places in the middle of your work. But then it says round your final answer to 1 decimal place. Okay, so no rounding down to 1 place until you're at the very end. Okay, so now what? Calcium levels are normally distributed. Good. That means I can make a nice, how much space do I have? A nice normal distribution. It's telling us that the mean of this distribution is right there, which I'm going to go ahead and show. Whoops, let's make this black first. There's my mean right down center, and that mean value is 0. Nope, that's not true. The mean value is nope, that's not true either. 9.5. Now what? So this is a little different. This is different than anything we did before up to this point. Individuals with calcium levels in the bottom 10%. The bottom 10%. They're talking about the area. This is 10% of the population right here. You could write that as a decimal, right? That's the area, okay, the bottom 10%. Now what we want is we want to know what this x value is, okay? The problem is I don't have a table that'll tell me that, but I do have a table that'll tell me the z value. Okay, so the z value for this, I got to look it up. Got to try to find something close to 0.10, and chances are it won't be exact, but we try to find as close as we can. So remember, I'm looking at the z table for a value of right here, 0.10, and this is in the body. This is the area of the area under the curve. So this is the body of our z table. Now this is to the left, so this is going to be a negative z table, and I'm really looking for, what color did I not use yet? Let's use purple. Looking for an area of 0.10. Where the heck is that? So I'm seeing, right, I'm starting to see it right here. I'm seeing 0.10, but then 7.5, 0.10, but then 20, 0.1003. Ooh, that's looking really good. 0.1003. That's close, very close to 0.10. So I'm going to go ahead and take that value. I go to the outside to see what is its z value, and its z score is negative 1.2. And then let's find the 100th place by going up here and seeing 8.08. So this is negative 1.28. So we found out the z value that's associated with the area to the left of around 10%, or the area to the left of being 0.10, which is 10%, is, let's see, gives us a z value. So this, what's associated with this point right here is this z value, which is negative 1.28. All right, what I want the x value. Okay, I got the z value, that's great, but I want the x value, the value that goes along with this problem, talking about calcium levels in people. I want to know the border right here, the border right here, which is between the people with these, considered to have these low levels with the other people, right? So I need to know what that x value is. I could use my z table, and that's what I did on the answer sheet. I just used the z value to do this, which is totally fine. We do have another formula that has it calculated for us, and maybe some people prefer to use that, so I'll use that. Once again, I could use the z value because it has all the variables, and I just have to solve. Now this guy is already isolating the x for us, so we'll go ahead and use this formula right here. Copy. Can I find it? I'm fading fast here. My coffee is starting to let me down. But paste, and it didn't work. Okay, let me write it down. The actual z value is, or the formula is, x equals, instead of using the z value, I can't remember what it is now because I always just use the z formula for that. And like I said, I'm fading fast here. X equals mu times z times, so I'm sorry, here it is right here. X equals mu plus z times sigma. Okay, but we have all those values, so this shouldn't be too bad. The mean is there in red, which is 9.5, plus the x value there in purple, which is negative, which is in purple, which is negative 1.28. And our standard deviation, I think, was given somewhere. Let's make that green. Standard deviation is 0.3. So when we multiply that and then add the 9.1, we get x is approximately equal to 9.116. It says, please give me the answer to round it to 1 decimal place in the final answer. And so that means the answer is 9.1, and these are mg over dLs. All right, let's see. We're now on to number 13. Number 13 says, the producer of a weight loss pill advertises that people who use the pill lose after 1 week an average. So this is going to be the population mean, right? Because it's coming from the maker that's done all this work. They didn't say anything about a sample. So this, we really need to make sure that we know that this is the population mean. And so that we use the proper notation as mu equals 1.75. And if we use the proper notation, then it works well with our formulas. With a standard deviation, so still didn't say anything about a sample. So this is our population standard deviation, which the appropriate notation for that, for the population standard deviation, is sigma, is 0.95. All right, we read on. It says in a recent study, a group of 60 people who used the pill. That's starting to sound like a sample, isn't it? So I'm going to go down here and say n equals 60. Who used this pill were interviewed. The study revealed that these people lost a mean of 1.77 pounds after 1 week. Well, now we're talking about, I'm going to run out of colors, aren't I? This is the mean, but who's it the mean of? It's a mean from these 60 people. That's called a sample mean, right? So that's called a sample mean. So let's pull that information down here. This is called a sample mean x bar. 1.77 pounds after 1 week. If the producer's claim is correct, what is the probability that the mean weight loss after 1 week on the pill for a random sample of 60 people, 60 individuals, will be 1.77 pounds or less? Okay, this gets a little bit confusing, I think, because it's more of a word problem. But this is talking about the central limit theorem, where we have a sample, and we can take we can actually, well, first of all, if the sample size is greater than 30, and it is, that we could use the central limit theorem, which says, and let me highlight it, and let's see what color am I going to use. I think I'm going to use red. It says that the mean of the sample means is going to be equal to the population mean. So that's really important for us to know, that the mean of the sample means is equal to the population mean. So that's going to be equal to 1.77. 1.75, what they gave us at the beginning, the population mean. Also, what's important to know is the standard deviation. So the standard deviation, the standard deviation of the sample means is just going to be the population mean divided by the square root of sample size. So now we get our standard deviation of our sample means. It's going to be equal to the population mean, which was given at the beginning to be 0.95 divided by the square root of the sample size we had over here in gold, 60. So then we do the math, and we get the standard deviation of the sample means to be approximately equal to 0.122644. Okay, so I'm going to run out of some space here. Let's see. I think I could do it. Let me draw a picture, because you know I'm kind of a picture freak. I like to see what's going on. I like to kind of explain things that way. And here's what's happening. This is going to be the distribution of sample means. And so the mean of the sample means is in red, which is 1.75. Now what they're asking us here is, let me put it in blue. After 1 week of 1 week on this pill for a random sample of 60 individuals, will be at 1.77 pounds or less. So what we're looking for is 1.77 pounds. Now 1.77 is to the right of this. I'm going to write here 1.77 is to the right of the mean. So let's kind of go like that. And it said 1.77 pounds or less. Well, that's to the left. How awesome is that? Because that'll match up with when we look it up on our z-table. Now, we need to convert 1.77 to a z value. No problem. That tells us the formula right there. It's going to be x bar, so our sample mean that we're talking about, which is 1.77, minus the mean of the sample means, which happen to be in red, 1.75. We do need to subtract those two and then divide it by the the standard deviation of the sample means, which was 0.122644. We find the z value of that, and that's going to be approximately 0.16. So this z value is approximately 0.16. We look that up on our z-table, and we get the answer. The area to the left is 0.5636. They said round to at least 3 decimal places. Okay, if we go to 3 decimal, it says at least 3, so 4 is fine too. But if I chopped it down to 3 decimal places, 0.564. But it said at least, so you can go more if you want. All right, number 14. Okay, so when I see things like this, something that says the mean of the sample means, I am tempted, and more than tempted, I would rather write it like this: the mean of this, the mean of the population, the sample proportions rather. Let me say that again. It says find the mean of p hat. P hat is the sample proportions, so that's mu of the sample proportions. And if I do that, it matches my formulas and just makes life easier. Let's continue here. It says 12% of the world's population is left-handed. Ooh, that sounds like a population figure, doesn't it? 12%. Now remember, 12% is a proportion. That's 0.12 or 12 hundredths or 12% of the world's population is left-handed. That's the population proportion for left-handedness, if that's a word. And remember that we do have the central limit theorem for this. And like I said before, they don't really go into the details of satisfying the assumptions, but we can do that by multiplying the sample size of 1,650 and times p, which is 0.12, and see if that's greater than or equal to 10, and then do that with its complement. And it does satisfy that. So we're going to continue. But really, what I wanted to show is this, that it says that the mean of my sample proportions is equal to the population proportion. So that means I already know the answer here. The mean of the sample proportions is equal to the population proportion, which was given right up here at 0.12. Now we want to get the standard deviation, and so I'd like to use the proper notation, standard deviation of the sample proportions, because I've got it right there. So if I do that, I take the population proportion, which happens to be what? 0.12 times its complement, 0.88, divided by the sample size, 1,650, and then don't forget to square root that. All right, when you do all that and then take the square root finally, you get approximately 0.008. Okay, so let's use that information to see if we can answer this question now. It says compute an approximation for, and this, the way this is read, use another color. So I'm looking for the probability of the p hats that are less than or equal to 0.14. So what we have here is a distribution of our sample distribution, and this is of p hats, which are sample proportions. So what I'm thinking here is I'm seeing something like this. Where do I have space to do this? I think right here. If it'll work. So this is our sample distribution. Of course, these are our p hats. And we know that the mean of the p hats was our part A to that question, which happens to be 0.12. And we also know that the point of interest is this blue. What's the probability? So it says, what's the probability that p hat is less than or equal to 0.14? I need to go to 0.14. 0.14 is about here. 0.14. Ooh, that's small. That's to the right of 0.12, so that's got to be there. And it says, find the probability that these p hats are less than 0.14. Well, less than is going to be to the left. So if I could figure out the area of that, I'd be in great shape. I do need to know the z-value, and it's not a problem because we got a formula right there. Highlight it with my little laser lighter, whatever they call that. See, it goes away. It's called the laser pen. Anyhow, I take the z-value, and it says take your p hat, which is the point of interest, which is this blue 0.14, subtract it from my mean of the p hats, which is the red 0.12. Take that and divide it by the standard deviation of the p hats, which we got that in part B, 0.008. Now we calculate it and we get a z-value of 2.5. This is 2.5 is our z-value that's associated with 0.12 in this problem. I'm sorry, 0.14 in this problem. I look up 2.5 and that's going to give me my area to the left. When I look it up on the table, I get my answer. And that answer is 0.9938. There's my answer. Moving on. Flip the page and we've got number 15. Poof, we're finally to the final stretch. See, I used to do this all the time when we were in the pandemic mode, but now that I'm teaching in person, I lecture like 6 or 7 hours a day. So it's really hard to do these videos on top of it. When we were in pandemic mode, I was not going in person. So lecturing, doing videos was great because I just lecture and then I didn't have to go in at the same time. So I'm struggling a little bit trying to do both. But hopefully you'll appreciate this, and hopefully this will improve test scores. Number 15, it says the lifetime of a certain brand of battery is known to have a standard deviation of 16. So if it's known to have a standard deviation, first of all, it's not saying that that's coming from a sample. So this is a known, this is a sigma, a known standard deviation of the population. Suppose that a random sample, now we're talking about a sample. So now we're talking about a sample. So, maybe we want to say, put a little note over here, n equals 70 in the sample. Suppose that a random sample of 70 such batteries has a mean life of 38. Now that comes from the sample, mean life of 38. That means it's a sample mean. X bar is 38. Based on this sample, find the 95% confidence interval for the true mean life of all batteries of this brand. Then give its lower limit and upper limit. Okay, so basically our confidence interval. So we're trying to find a confidence interval once again for the true mean life. We're looking for the confidence interval of this population, and we have sigma. Let's just be really clear. What's the formula when you have sigma, the population standard deviation? The formula is this guy right here, because we know sigma. Okay, so let's go ahead and use this formula in sigma. And also a notable thing is its critical is a z value. Okay, let's get back and finish this thing off. So what do I need? I already have its critical. X bar is 38. I need to figure out I don't have its critical. I have its point estimate, which is X bar 38. Now I need its critical. Remember, its critical is C sub half of alpha. I looked that up because that's for a 95% confidence interval. And when I look up 95% confidence interval, 95, it's the same guy that we had before, which is 1.96. So we get 1.96. Okay, so now I need to find the standard error. Remember, we could find the standard error. Let me write it up here, standard error. So standard error is just going to be 16. Remember our sigma, 16 divided by the square root of our sample size, which is 70. Let's call this the standard error. So what is the standard error? It is approximately 1.9123657 goes on. Okay, now let's go ahead and find our margin of error. Margin of error equals the critical of 1.96. That gets multiplied by the standard error we found to be 1.912. I got lost, my eyes blinking. 1.9123657. All right, now we've got our margin of error approximately what? Approximately 3.74823736. See how many decimal places I'm using? You don't have to use that many. It says carry. So let me just kind of clarify. Carry your intermediate computations to at least 3 decimal places. So on this one, they want at least 3 places. They want at least 3. I went way overboard because I'm just high achiever. But anyhow, it says at least 3 decimal places. So there you go. That's all you had to really use. And then it says round your final answer to 1 decimal place. So you're going to use at least 3 decimal places when you're working it. and round down to one place in the end. We didn't use 3 places here because it was given it was 1.960, so it's the same thing as 1.96. So now let's go ahead and find our confidence interval. We start off with a point estimate, which is 38. Then we have to add, or I'm sorry, subtract the margin of error. I'm so tired, I'm just going to copy it again. Hopefully it works. Copy, 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 paste. There it is. Work like a charm. And remember, we're trying to find the population mean. We're trying to get a confidence interval for the population mean. And then on the upper limit, that's just going to be our point estimate of 38. And we need to now add the margin of error. And what just happened? Oh man, come on. Lost it. I can't control it. Get out of there. Let me try again. Paste. Oh. There we go. I can do it. Okay, let's go ahead and subtract the 2, and it says round to 1 decimal place, so I'm going to get a 34.3. And I add, and I'm going to get round to 1 place 41.7, and this is at a 95% critical or confidence level. Okay, so there's my solution to this problem. Good thing there's only one left because I'm about ready to pass out. Number 16, it says a coin-operated coffee machine made by Big Corporation was designed to discharge a mean of 8 ounces of coffee per cup. Okay, designed to discharge. So if they do a bunch of them, the mean should be 8 ounces per cup. If it dispenses more than that on average, the company will lose money. And if it dispenses less, the customers will probably complain. Big Corporation would like to estimate the mean amount of coffee mu dispensed. So this is mu, which is, they're looking for, where's my highlighter? Would like to estimate the mean. Big company would like to estimate the mu, which is the population mean dispensed per cup by this machine. Big will choose a random sample of cups amounts dispensed by this machine and use this sample to estimate mu. So we're doing a confidence interval. No, wait, I'm not sure what. Well, right now, all I knew was we're doing a confidence interval, trying to estimate mu. Assuming that the standard deviation of cup amounts dispensed by this machine, so we're assuming that a standard deviation is 0.4. So let's make that green. What is the minimum sample size needed for us to make a 90% confidence interval, or a confidence interval that estimates mu within 0.08 ounces? So that is telling us that this right here, when you estimate within this many ounces, that's our M, which is our margin of error. Margin of error is 0.08. All right, so we take a look at our sheet, and unfortunately the sheet that I printed out for everybody, somehow just this formula disappeared off it. Somehow it just, I don't know what happened anyways. So, during the test, I'm going to make sure that's on your sheet. I'll put it on the board if it's not on your formula sheet that's given out at the class. But that formula happens to be this one right here. It says sample size equals our critical z sub half alpha times our sigma, population standard deviation, divided by margin of error m, and that gets squared. So no problem, we can do this. We have all the information needed. N equals, well, we're going to need We're going to need a critical. For what? A 90% confidence interval. Let's go see if we can figure that out. Here it is right here. 90% confidence interval right here. And so therefore the critical is right there. That's our z sub half alpha, which is 1.645. Let's go ahead and put that in over here. 1.645. That gets multiplied by our sigma, and I made my sigma green. So there's the green sigma, and there it is right there. So this is multiplied by the sigma, which is 0.4. And the formula says divided by the margin of error. Our margin of error was given, our margin of error, if I can change the color to the right color, is 0.08. So now, when I multiply and then divide, and don't forget to square it in the end. And when you do all that, you should get approximately 67.650625. Now, what are we doing? We're doing, we need to know the sample size to obtain a margin of error of 0.08 and a confidence level of 90%. So it's saying you need a sample size of 67.6. Well, I can't get like 65% of a cup. So if I drop it down to 67, I don't have the sample size to achieve my goal. I always have to go up to the nearest integer. So the answer is going to be n equals 68. So the minimum sample size is 68. And that'll do it. That is our review. I hope that helps. I hope you appreciate this because I am dying. I'm tired. I'm sleepy. But if everybody can watch this, if they have questions, they can go back, slow it down, listen to me a million times, whatever you need to do to get a great score on the next test. Good luck, everybody. Take care. Hope you have a great one, and goodbye.